Welcome to today's webinar. The topic today is comparing web service and in-app scripting using Python in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, the German and English webinars, newsletters, content of the website, and so on. I will be the moderator today, and I will also answer your questions together with Thomas Günther. And the presentation will be done by Rebecca Goebel. She works in our team in the customer support, and she's also responsible for the development of the web service add-on. Thomas Günther, who will support me by answering your questions, is also working in the customer support team, and he is very familiar with the add-on web service. Okay, for the attendees who participate the first time in the Dlubal webinar, I say something how you can ask questions. At first, I switch off my webcam that you can see the full screen. Just press that button with the question mark, then enter your question in that field, press send, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Rebecca. Rebecca, it's your turn.
Thank you, Andreas, for the introduction. In this webinar, I'm going to present you our web service as well as our in-app scripting with Python. In the beginning, I will point out the differences between both. Afterwards, I will show you an example on our web service where I will do a parametric study on a steel hall. Then I will present you another example on how to use in-app scripting. In that example, I will create a GUI using PyQt. And in the end, I will share with you some prospects about our latest development, the API 2. But first of all, I would like to point out the differences between web service and in-app scripting. Web services are a type of application programming interface, so-called API, where an XML-based information exchange is used. Our web service offers certain functions to communicate with RFEM in Python and C#. The communication with RFEM is done via a server, and therefore an internet connection is necessary to use web service. Via web service, it's possible to create the geometry, start the calculation, and also read out the results. So it's basically possible to access nearly every function from RFEM via web service. Using web service, the script is started from outside RFEM, for example from a programming environment like Visual Studio Code. In-app scripting, on the other hand, is embedded in RFEM and enables a direct communication with RFEM. Therefore, its usage does not require an internet connection. Using in-app scripting, the script is started directly inside RFEM via the script manager. That is why no external programming environment is needed. This makes the scripting well suited for programming beginners in order to make first modelings with Python and to get started without having to deal with some programming environments. The scripts for in-app scripting can be created in Python or JavaScript. And however, scripting in RFEM offers many possibilities, but it does not offer the full range of functions that the web service can offer you. Only structure objects can be created, but it's not possible yet to start the calculation or read out results. That's why web service is more suitable for more complex use cases. Moreover, the in-app scripting does not use the same high-level functions of web service, but an own similar syntax that I will show you in the second example. So then I would already switch to the first example. In this first example, I will create the whole geometry of a steel hall using our Python web service, and afterwards I run a parametric study to find out the maximum span so that the deformation limit is not yet exceeded. So then I will switch to my Visual Studio Code. So in Visual Studio Code I already installed the RFEM library using pip install RFEM, and as you can see, I also already imported the parts of our library that I will need in the script. And here in the beginning I also already created a new model and defined a variable for our span, which is 4 meters for the beginning, which we will optimize later. And I also created a material and 2 different sections. For the material and the section name, the name corresponds to the name in the material or section library of RFEM. So now I will create a while loop with while true. This while loop will then run as long as the deformation limit is not exceeded. So we will define a break criteria later on. But first of all, I define another variable for the middle coordinate, which is in the middle of the span, so 0.5 times span. And I need some more variables, one called m and n, for the loops. And the last variable I'm defining is frame distance, which I set to 0. This is the distance between each frame. So as you saw in the presentation, I will create a steel hole containing 3 frames, and this distance will be the distance between each frame. So now I'm creating a for loop for I in range 3. It's a loop over 3 iterations because I'm creating 3 frames for the whole. So in this loop I can now create the geometry of 1 frame. I'm copying this here, and yeah, as you can see, it's as always the node is defined by a node number, then the x coordinate, y coordinate and z coordinate. The only difference is that I'm setting my variables instead of absolute numbers. Okay, now I have all my nodes created, and now I will create the members. So first of all, I'm creating 2 different members for the columns, then 2 members for the beams. And here it's also the same. The first parameter stands for the number of the member, then the second parameter is the start node, then the end node, the section rotation, and the section that is used for the member. Okay, and then I have an if statement here because I want to create members for the longitudinal bracing, and I only need those members when I'm when I already have 2 frames or more. So that's why I need this if condition, that the members are only created from the second loop on. And in the end, I'm increasing my variable m by 6 because I created 6 members and yeah, want to go on with the numbering in the next loop. If I don't use longitudinal bracing, I only increase it by 4. Okay, then afterwards I'm also increasing my variable n for the node numbers. and the frame distance, I changed the value by 3.5 meters. Okay, so now we are already done with the for loop, and we can create the other parts of the geometry that are missing. So now I want to add a nodal support by using nodal support class, and I specify the number of the support, and now all nodes where the support should be. I want the support to be on each bottom node of the columns. So those are the nodes 1, 2, 6, 7, 11, and 12. And in the end, I specified the type of the nodal support by nodal support type hinged. So it's a hinged nodal support on the bottom of the columns. Now I'm finished with the geometry, and now I can specify another load case. So when creating a new model in RFEM, load case 1 with the self weight is already created, but I want another load case for snow. So I copy this again. Yeah, here I specify the number, then the name. Self weight is not active, and the action category type accordingly. So if you're starting with the Python library and you're not sure what's the correct name of your corresponding action category, you could create the load case in RFEM itself and afterwards read it out with Python, and then you can easily see what's the correct full name of this action category. Okay, so now I will add 2 member loads. The first member load is applied in load case number 1. It's applied on all beams of the hall, and load direction is in Z direction, and the magnitude is 1 kilonewton per meter. The second member load is applied in load case 2, also on the beams of the members of the hall, and this time the magnitude is 4 kilonewton per meter. Okay, next I'm creating a design situation. Here I also only have to specify the number and the design situation type. And the last thing I'm creating is 2 load combinations, and here I'm specifying the number again, then the analysis type, it's static analysis. Here afterwards I define the design situation where the load combination applies, and lastly I define the combination items. In this load case I use the factor 1.35 times load case 1, and in load combination 2 I use 1.35 times load case 1 plus 1.5 times load case 2. Okay, so now we defined all our objects that we need, and we can calculate all so the whole structure, every load case and every load combination. And once the calculation is done, I want to read out the deformations. So I'm creating a variable deformations where I can save these results. And to access the deformation results, I use the function result tables dot members global deformations, and I hand over the case object type, which is the loading type. So I want to read out the results of the design situation, and it should be design situation number 1, and the last parameter, there I hand over the 0 because I want to read out the results of all members at once. Next, I want to see the maximum deformation. So I want to filter this table for the maximum deformation. Therefore, I create another variable, max deformation. And now I can use our high-level function getMaxValue to get the maximum deformation. Here I have to pass in the results that I want to filter and the column of the table that I want to filter for. So it's the displacement absolute that I want to have at a maximum, so that's why I'm passing this here. And I'm also multiplying it by 100 that I have the maximum deformation in centimeters. And in the end, I also want to round this value to only have 2. Okay, and the last variable that I need to define is the deformation limit. So I'm calculating this by span times 100, so the span in centimeters divided by 300. So my deformation limit value is L divided by 300. And now I can define my break criteria for the while loop. So I define an if statement. If the maximum deformation, if max deformation is greater than the deformation limit, then I want to print a statement to the console. Sorry. I want to print out the maximum span, and this is equal to the span of the last loop, of the previous loop, because in this loop the deformation limit is already exceeded, so that the span is not valid anymore. Okay, and when I did this, I can use the keyword break to exit from the while loop. Okay, but in case this if condition is not valid in a loop, then I want to print out another statement to the console. I want to display there the current span and the according maximum deformation. And the last step in each iteration of the while loop is to increase the variable span by 0.5 meters. So we created a while loop which is running until this if statement is true. So once this if statement true, the loop is finished and we found the maximum span. Okay, so now when we did this, I will show you how to run the example. So we see the connection to the server is already done. And now a new model has been created and each part of the structure is being created. Now the calculation is done, and now we see that the geometry is adapted according to the new value of span and frame distance. And we also see our print statement works, and we see in the terminal the current span and the according maximum deformation. And now we have reached the end, so the maximum deformation, the maximum span is 5 meters with a deformation of 1.34 centimeters. Okay, then I would like to show you another way to optimize a structure. Therefore, I already prepared another model. And if you have an existing alpha model, it's also possible to use the global parameters to modify the structure and to do a parametric study. So here I have the global parameters, and I already defined 2 values. The first global parameter is named span, and the second global parameter is named like our middle coordinate from the Python script. And I defined the span as a value and set it to 4 meters, and the middle coordinate is of type formula and is calculated by 0.5 times span, like we did it in our script manually before. And now that I defined those global parameters, I can adjust my node coordinates. So I edit all these nodes, and via this arrow I can edit the formula, and here you can see I already defined this value to be the span. And for the middle coordinate I'm doing the same. And here I already prepared it and set the middle coordinate, which is half of the span. And now that we have our global parameters inside the model, we can use this simple script to optimize the structure. So the script is connecting to the current model, and then the first global parameter span is read out and saved in a variable called span. And then in a for loop with 3 iterations, the value of the span is increased by 0.5 meters in every iteration, and afterwards the global parameter is set again. So if we go back to this table, the script is only changing this column here, the value of span, and by setting this parameter again, this value is changed in this table. And in the end, everything is calculated and the results are exported as a CSV file, so that I could later on evaluate the results and see which span is best suited for my use case. So when I now run the script, okay, I have a small typo here. Yeah, we see that the geometry was adapted, and now the calculation is done, and the results are exported as CSV, and again the geometry was adapted. And as you can see, this is a very easy way to modify existing models with the help of Python with a minimum effort. And yeah, I think this is a really good way to do a parametric study on your existing models. Okay, then I would switch to the second example. In this second example, I will show you how to create this GUI using the PyQt library and our in-app scripting with Python. So I will create several input fields to define the number of spans and the span, and to choose from a selection of sections. And this will then create a continuous beam with a member load. Okay, then I'm already switching to RFEM. And first of all, I switch to an empty file, and I will show you how to display the script manager here. And I will also display the console and switch to Python in both. So in order to be able to use PyQt afterwards in our example, I first need to install it into the RFEM environment. So I click on the black button and I use the command python -m pip install PyQt 5, and after that PyQt is installed in the environment of the script manager in RFEM, and I can use it in my script. So as you can see, under the user scripts there are already some scripts defined. I will show you how this example should look like in the end. Okay, and these user scripts are saved under the following path. So it's under the user in app data local and Dlubal, and then the user scripts are saved in the RFEM folder from your RFEM version that you are working in under user scripts. There you can find all your scripts, and the scripts also need to be saved there in order to start them from the script manager in RFEM. Okay, then I will create a new script for this example. And you can see it's already here under the user scripts. But as it is empty, I will right click on it to edit it. And then my Visual Studio Code or any other text editor program will open. So if you don't have Visual Studio Code, it's no problem. You can also use each other editor. So first of all, in this example, I'm importing the PyQt library and each part that I'm going to use in this example. And in the next step, I'm creating a class dialog, which will contain all parts of the dialog window, all objects and all functions that are related to the dialog. In there, I first define an init method. Yeah, this method will just call the init UI method, which we are now creating. Okay, so the initUI method will contain all parts of the GUI, so all input fields, all text, all, the button, and so on. And yeah, that's it. And I start by creating a variable called widget, and I set the variable to QDialog, which is basically our main window of the application. Afterwards, I create another variable called layout, and I create this by using the PyQt class QGridLayout. This class will divide the window in a grid, and this makes it pretty easy to set our parts of the GUI on a specific position. Okay, now next I can do some window settings. So first I set the geometry of the window, and here the first two parameters define on which pixel on related to the screen the GUI should appear when I start the script. And the third and fourth parameter define the geometry of the window itself. Next, I also want to create a title for the window. I use set window title. Okay, and now I'm creating the first object of my GUI, which is a so-called label. So it's the text that is displayed in the GUI. So I first create a variable for this label. I call it label span number because it's the label for the span number. And by using QLabel, I can hand over the text that should be displayed in this label. And I do the same thing for span and section. And now I have these three texts displayed in the GUI. Now I want to create the input fields. So as you saw, I have two input fields to input the span number and also the span. So I create a first input field called span number, and I can use the class QLineEdit, and this simply creates the input field. I do the same for the span. Okay. And now, as you saw in the example GUI, I have a combo box to select from different sections. I'm creating this one now, and I again define a variable for this combo box, and by using QComboBox I create the combo box. But now at the moment this combo box is completely empty without any item. This is why we need to add certain items to the combo box now. We do this by self.section.addItem, and here we can pass the section name. And I'm also doing the same for the other section names. And now I have 4 different options in my combo box. The only thing that is now missing in the GUI is the button to start the model generation. So I'm creating it now, and I define a variable called button start and use the PyQt class QPushButton, and in parentheses I can define the text that should be displayed in the button. So now we have a button, but nothing happens when we click on it because no function is connected to the button. So in the next step I'm connecting this button to a function. Use .clicked.connect and hand over the function name. And this function does not yet exist, so we need to create it. And we create it also in the dialog class. So I define a new function. And here I'm simply handing over the input from the input fields and save it in a variable. So I define a variable called span number and hand over the text of my input field from the span number. Self.spanNumber.text, and I want it to be an integer. So everything that is inserted into the input field is a string, but I want it to be an integer, so I change the data type. And I'm doing the same for span and for section. The only difference is that for the combo box I need to use current text instead of text. And in the end I need to use self.accept to activate the button. Okay, now we defined every object that we need in the GUI, but we also have to add these components to the window. So I do this by saying self.layout. Layout is our variable that we defined in the beginning, and add widget. And here I pass the variable name of the object. So in this case I add the label for our span number to the GUI, and in the second and third parameter I can define where it should be positioned. So as I created a grid layout, I can define in which row and which column the object should be positioned. Here I hand over 0 and 0, so that means that the label for our span number is situated in the row number 0 and column number 0, so it's situated in the left upper corner of the window. I'm doing the same for all the other objects and only varying the number of the row or the column. And for the button, you can see I defined more parameters here. So this this button is positioned in row number 4, column number 1, and the next parameter is the row span, so it defines how many rows should be how many rows the button should span. In this case it's just 1. And the next parameter is the column span, and I defined it to be -1, which means that the button should span until the right edge of the window. Okay, now the layout is ready, and the only thing we need to do is to activate the layout. We do this by self.set layout and hand over our layout variable. Okay, so now the GUI itself is finished, but we need to define some more functions to connect it to the rest of the application. So I define another function called getSpanValue, and this just returns our variable span number, and it returns the variable for span number. And I do the same for span and section. And now we are finished. And now I go to the main program, and I need to fill these variables again in this place: span number, span, and section. And to do this, I use another function called getValues, which I will define now. But this function is not located inside the QDialog, inside the dialog class, but outside in the main program. And here I'm first initializing the GUI, because at the moment we have this GUI, but it's never initialized or started, so we don't see anything if we start the application. So I'm defining a dialog variable called dialog, and I call the dialog class here, and afterwards I execute this dialog. In the next step, I'm filling the variables for span number, span, and section in the main program, and I do this by calling the accordingly function inside of the dialog class. So for span number, I call getSpanNumber, and I do the same for span and section. And in the end, I return those values. Okay, so now we have access to the input from the input field in our main program, and we can start to create the geometry. I do this by using a try except statement, and I do this to be able to debug the code later, so that I have some idea what went wrong if something is going wrong. So if something happens during the geometry generation, I want to print out this message, and this message will be printed out to the console in RFEM. So the console is very helpful in this case for debugging your code from in-app scripting. Okay, but in the try block, I'm now defining a material using the syntax for the in-app scripting. So I use materials.create. I pass the number of the material and also the name of the material, which is this one in my case. Afterwards, I'm defining a section with sections.create standardized style. It's section number 1, and as name I hand over our section variable from the combo box. In order to find the right functions in your case, it's very helpful to use our Python export function, with which you can export your RFEM model as a Python script, and then you see exactly how to define your objects in the in-app scripting or via the console also. Okay, in the next step I'm creating a first node via nodes.create standard. And I'm also creating a nodal support via nodal supports.create. I hand over the number of the nodal support 1. A user-defined name is enabled. The name is hinged, and I want the node to be on nodes only number 1. And here I define the spring and rotational restraint conditions. Afterwards, I will define some help variables, node no, and set it to 2, which is the node number. Then another variable for the member number. And I'm also creating a list, nodes list, which will contain all the node numbers, or some node numbers. You will see it later on. Also a list for supported nodes, which will contain all node numbers of nodes which should get a nodal support. Then member list, which will contain the member numbers. And I will already add to my nodes list the first node number, but as a string. Okay, and now I'm creating a for loop again for I in range span number in this case. And here I'm creating a second node. I'm using the same function as in the beginning, but I change the node number to our variable, and the span is also variable because I don't know how many spans the model will have, as it is user defined in the GUI. Okay, afterwards I'm adding this second node number to our nodes list. And also to the supported nodes. Okay, and now I could define a line by using the function lines.create polyline. And here I could pass in the number of the line and the nodes which are defining the line. I would do this by a comma separated string. But as I'm doing this in a loop and the nodes are changing in each iteration, I need some solution here, and I'm using so I'm converting the string I'm converting the nodes list to this comma separated string, and I do this by using the .join method. I say join every element of the list by a comma, and I pass my nodes list. And now I can use this variable node string in the line function, and the line number should also be with I plus 1. Okay, now I'm also creating a string for the line number, which I will need to define the member. Okay, now I can create the member by using members.createBeam. I pass in the member number, and for line I set the line string. Okay, and afterwards I'm adding this member number to the member list. And in the end of the for loop, I'm emptying the nodes list, because in the second iteration it should not contain node number 1 anymore, so I'm changing this here. So I'm first emptying it, and afterwards I'm adding the second node or the current node number. Okay, and I'm also increasing the node number, the member number, and that's it. Now I'm finished with the for loop, and outside of the for loop I want to create another nodal support. But to do this, I first need another help variable called support node string, and I use the join function again to create a comma separated string from my supported nodes list. Okay, and now I can use this in the nodal support function. Okay, so this is basically the same function as in the beginning, but I don't have to define the user-defined name variable or the name if I don't need it. So here I only hand over the nodes and the spring and rotational restraint conditions. Okay, so now I'm already finished with the geometry generation. But I also want to add some loading to the model, so I create another try except block to be able to see if something happened during the load generation. Okay, and now I first create some static analysis settings by using static analysis settings.create, and I only want the standard settings, so I don't have to pass any parameter. After that, I'm creating a load case via loadcases.create, it's a self-read load case, and I define the static analysis settings to be the settings number 1. For the second load case, I create a load case for snow, and here I have to define the action category because the standard is a permanent action, but here I want to use a different one, so I have to define this parameter. And I could also define a comment here. And again, it's really helpful to use the Python export to see how it's done and to see which action category name you will need for your case. Okay, now I'm creating another help variable called member string, and I use the join function again, but this time with my member list. And I need this to be able to create a member load which is situated on each member that I created before. So I create the member load via load cases, and in the parents I'm defining the load case number, and I say dot member loads dot create force. I pass the number of the force 1, then the member string, so all members that have this member load. Then I define the load case. It's load case 2. And for the load direction, it's a bit difficult again, but by using the Python export, you can easily see what's the correct name for your load direction. And at least I define the magnitude and set it to 2 kilonewton per meter. Okay, and now I'm finished with the code. All the model generation is done. And now I can switch to RFEM and try to run the script. So we see the GUI works, at least, and we can define a number of spans, the span, and also select one of these sections. And by clicking Start, we see now that it was very helpful to use the debugging function. So we see something went wrong by creating the geometry and also by setting load cases and combinations. So in the next step I could go back to my script and look what's wrong. Most likely there was some typo in any function. But for now, for this example, I'm gonna show you the prepared example. I'm passing in the variables again, and when I click on the button, the geometry is really fast created, and we also have the 2 load cases with the member load in load case 2. And now we could start a calculation in RFEM and do further analysis inside of RFEM. And finally, I'm happy to present you our new development, the new version of the web service. API 2 describes a new generation of web service and API, and while the current web service solution is using the SOAP technology, the new API will be based on the gRPC technology. With the SOAP technology, the data is exchanged in XML format, while with gRPC technology, the messages are exchanged in binary format. Moreover, the newer HTML2 protocol is used, which also contributes to a more efficient data transfer. This new technology enables a data transfer that is up to 10 times faster than before. In addition, using the batch function, several objects can be combined in a list and then passed together, which also increases the efficiency. For example, you could bundle all base objects in a list and transfer them to RFEM as a complete package. I will also show this in a small example later. As part of the new API, the syntax of the web service, in-app scripting and the console will be aligned so that you no longer have to consider any differences between the three formats in the future. Furthermore, the authentication will also take place via an API key. This can be helpful, for example, to differentiate between different API keys within the company and thus between different projects. There will also be an innovation in billing. With the current web service, billing is based on an annual subscription. In addition to that subscription, the new web service will have a usage-based billing model in which only certain functions will cost additional credits. Fortunately, the first version of the new API is expected to be released by the end of this year. However, the current web service solution will still be usable. And now I would like to show you a first small example with the new API. So first I would like to show you how you can create your API key. You can do this via your extranet account under My Data, and on the bottom there will be a section API 2 where you can create a new API key here and save it. So it's possible to have multiple API keys at the same time. I already created an API key in the past, which I'm using in this webinar. So again, for this example, I'm using Visual Studio Code, and here I already pre-installed the RFEM library. So there's going to be a new pip package which you can install in the terminal, like you did this for Web Service 1 also. So here in the beginning you see I'm again importing all parts of the library that I'm needing, and down here I create a new instance with RFEM. I pass my API key for validation, and in here I can do all the communication with RFEM. And the next function, client.createModel, is creating a new model in RFEM. Here I have to pass rfem.application.createModelRequest and hand over a name for the model. Afterwards, I'm using the batch technology and I'm creating a list called structure, which will contain all structure objects of the model. So first I created a material, and I only have to pass the number of the material and the name. So you see it's pretty similar to the current API. And secondly, I'm creating a section via rfem.structureCore.section. And you can see it's also similar to API 1. You can either use this type of coding, or you can import the class material, for example, by doing this here. And you could do the same for section also, or for node, and so on, so that you don't have to use this long structure every time. Okay, but for the section I also only need to define the number, the name of the section, and the material. Then I create the first node. Here I only have to pass in the number because the default coordinates are again 0, 0, 0, and I don't need to define them. The second node has node number 2, and I only change coordinate 1, which is the x coordinate, and set it to 3. In the next step I am creating a line, and I pass in the number of the line and afterwards the definition nodes as a list. And the last part of the structure generation is the member. Here I define the member number, afterwards the line on which the member is defined, and the section at the start of the member. There are also many more parameters, which you can see when I'm hovering over this member class, and which you could also define if you want, if you need a different value than the default value. Okay, now my list is finished, and I use the function client.createObjectList and hand over my structure list, and this command is handing over all these objects at once into RFEM. Afterwards I use client.updateObject to update an existing object, and in this case I'm updating the nodes on which the nodal support should be. So I set nodes to 1. In the next step I also want to add some loading to the model, and here I'm creating another list called loading, where I'm bundling all the loading data. And I'm creating a load case with rfem.loading.loadCase, and I give it a number and a name. And in the second step I'm creating a nodal load with rfem.loads.nodal-load, and I pass the number of the load case number, the nodes as a list again, and also the magnitude of the load and the nodal load direction. And when I'm done with this list, I can use the command again, client.createObjectList, and pass in the loading, and this will create both the load case and the nodal load in RFEM. And the last step in this script is to read out a member. Therefore I use the command client.getObject, and I pass in the member, and it should be member number 1. And I print out this member in the console to see all parameters of the member. So as you can see, there are only a few main functions in the API tool, like create object list, get object, update object. And you can specify them by the input parameters. Okay, and now I'm going to run the script. And you already see the connection is done, and a new model was created. And already the structure has been created, which was really fast. And we also have the 2 load cases, and everything worked fine. Okay, then I hope you got a good first impression about API 2, and I hope you could also learn some new things about our web service and our in-app scripting. And now I'm handing over back to Andreas.
Thank you for your presentation, Rebecca. A hint from my side to our online courses. There are 3 courses available. At first, the RFEM 6 course for beginners, the Eurocode 2 course for reinforced concrete design, the Eurocode 3 course for steel design. For more information, just click on the buttons at the bottom, or you can scan the QR codes, where are information about the content, the prices, and so on. The courses consists of several chapters. You can stop the course anytime and continue when you have time again. Okay, that should be also all from my side. I thank you for your attention. Thanks to Rebecca for the presentation. Thanks to Thomas for the support by answering the questions. I wish all a nice rest of the day. Bye-bye.